This is our high altitude weather balloon. High altitude weather balloons basically provide a lot of essential data for meteorologists today. They record a lot of information in the upper atmosphere. And basically, our objective was how can we create one to do this similar function? So, a high altitude weather balloon is basically constructed of the balloon, probably a pretty important part, as well as the parachute, and then it's attached to the payload or whatever you want to receive your information. Our particular project has a Raspberry Pi powering the system with ham radios, as well as a bunch of other sensors that it will send up into the atmosphere, about 100,000 feet up in the air, and then the balloon will eventually pop, and the whole time the system will be collecting this data, taking pictures, and even sending some data back down to us. In the meantime, the balloon will still be transmitting. It won't be a balloon once it pops, it'll just be a parachute with the payload beneath. And it will send all that information down to us, tracking it with GPS, telling us exactly where it's gone to.
When it comes to the sensors, we mostly used I2C interfacing form. Um, we sent up sensors to measure temperature, humidity, pressure, um, and then also light, UV, and then on the inside we also had an accelerometer with a gyroscope measure anyway to measure tilt and stuff on the inside, just because this thing gets thrown around a lot. We're wanting to know kind of how much. And so yeah, the idea was to collect as much data as we could. We then had it on boot up, save and log all that information so that we could either transmit it or when we recovered it, we could get all the information as well.
Scan TV portion of our project works by using two of the cameras on our payload. The first one is the Pi cam, which has a high-speed cable going right into the Pi. The other one we utilized was a webcam. It's shown on the back. It's hard to see. So the way it works is we take a picture and save it to the Pi's SD card, and then we convert it from an image to an audio file. And we're using the GPIO pin on the Raspberry Pi and a transistor to key up the radio, and then we play the audio file and have the cable go from the audio out of the Pi to the audio in on our radio, and it transmits the audio and transmits it over the air back to the ground station. So we were able to send live pictures from our high altitude balloon back to the ground. So we're going to demonstrate that right now. So I'm going to stand in front of this picture, and we've got a station over here to the left that we're going to show you it receiving and decoding the picture. Okay.
Code is running.
So the code's running. So you can hear the audio of the image. It sounds a lot like dial-up, and it's definitely slow. That's why it's called slow scan TV.
So finally, we have a APRS, ham radio APRS tracking system that we're utilizing. This is a T3 Micro, a little USB dongle that basically has a GPS unit, and it takes the GPS data and encodes the information into an audio frequency shift keying signal, which is sent over our second ham radio. And not only does it control the sending of those position packets, but we also have it integrated with a Pi so we can send telemetry. So basically, as it's flying, we can get data as far as temperatures and pressures and other portions of the sensor. So that's an imperative part of our tracking system. It's a key part in any weather balloon is to know where it's at, not only for tracking real time, to know how fast the wind's blowing and where things are, different areas, but for recovery of the system. So that's the primary tracking system integrated with Pi and self-contained. We also have, step this way, on the computer we have several systems in place for decoding the information. So the APRS position data is decoded in a program. This is just one example, APRS point. And so basically we would see the balloon tracked across the screen. We have a little TNC, terminal node controller, to decode the information from another ham radio. Another method that we've also experimented with is a little SDR unit. So we decode the information on the SDR, on narrowband FM signal, and then we pass it into a program that can convert that audio signal into the APRS packets, and then push it back for tracking and decoding and telemetry, and that's our system.